Okay. Good morning. My name is Clarence Fisfis. I'm going to give you an update on fast IGP convergence. So let's first define convergence. We have a traffic stream going from source to destination via the green path. So at a certain time t1, there's going to be a link failure along the green path. So at time t1, the loss of connectivity starts. At time t2, an alternate end-to-end path exists from source to destination. At time t2, the loss of connectivity stops. We define convergence as t2 minus t1, thus as the loss of connectivity duration. We're going to analyze convergence for IGP learned prefixes, and we are going also to analyze the impact of IGP convergence on BGP learned prefixes. Common sense typically says that IGP convergence takes from 10 to 30 seconds. The objective we set for ourselves with this project was to achieve sub-second convergence for the first 500 IGP prefixes and for the BGP prefixes that recurs on them, assuming obviously no BGP flaps. This presentation is given with ISIS. We have worked on ISIS and OSPF, and the principle applies for both IGPs. Here is our black box lab setup. The unit under test is the router with the yellow dots. It's a 12,400 router, which will be equipped with two types of processors, either a GRP or a PRP1, and the line cards are Engine 2, Engine 3, or Engine 4+. The router is running a pre-release version of 12.027s. We're going to test convergence in the bottom in the top to bottom direction. So what I'm going to do is to send traffic from A to B, and I'm going to cause a link failure, so triggering convergence. I send 10,000 packets per second on each stream. So if I count the number of packet drops, I can derive the loss of connectivity duration per stream. The granularity is 0.1 milliseconds. So I'm sending my traffic from A to B. The cloud that is faking a realistic ISIS topology is situated at the bottom of the picture. It's a cloud worth 1,000 ISIS node and 2,500 ISIS prefixes. As you can see, it's a worst case scenario, because when I'm going to fail the link from the unit under test viewpoint, all the cloud is impacted. So it means a full SPT will be required. Also, I inject 160,000 BGP prefixes in the lab setup. I'm actually sending 15 streams from A to B, 12 streams going to IGP destination, and then 3 streams for BGP analysis. The 12 streams for IGP destination are going to prefix number 1, prefix number 250, prefix number 500, and so on up to 2,500. This allows to monitor the convergence as a function of where you are in the modification list. The stream number 13 is going to be the BGP next up. The streams number 14 and 15 are going to 2 BGP destinations, so prefixes learned as BGP destination that recurs on the BGP next up in stream number 13. For each of the streams, we're sending 10,000 packets per second. The lab setup is convenient because I can test for 4 scenarios. If I fail this link or if I fail this link, I have respectively a local or a remote failure. And then depending if I set this to 200 or 300, before the convergence experimentation, I have load balancing or not. So I will always analyze those 4 scenarios. For each scenarios, we will repeat the test 100 times. So let us look at the results for the unit under test being equipped with a GRP processor and an Engine 2 line card. Yeah, all the interfaces are POS. So let us look at the results for a remote failure, no load balancing. The processor is a GRP and the line card is an Engine 2 POS. The x-axis gives you the prefix position in the update list. you see the 12 ISIS streams and then the 3 BGP streams. Just forget about the 3 last points for the beginning. So the x-axis is the prefix position, the y-axis is the loss of connectivity that was measured. For each test we repeat it 100 times. So I'm plotting 3 curves. In dark blue it's the minimum across 100 iterations for each stream. In pink it's the median, and in yellow it's the percentile 100 or the maximum. So what you are seeing here is that first the system is linear, the convergence process is linear. The initial delay is short, on the order of 150 to 280 milliseconds. The slope, which is coming from the prefix-dependent update, is much more important than the initial delay. The initial delay is made of the link failure detection, the LSP origination, the LSP flooding, and the shortest path tree computation. This represents 150 to 280 milliseconds here. Then the prefix-dependent process is going on that updates the RIB and FIB tables. And you see that it's more expensive, much more expensive than actually all the other components of a convergence event. That's why we have introduced a prioritization capability that allows the designer to flag prefixes in the IGP as being either important or not important for the convergence. And so the important prefixes always converge first. That's why you see the red fig bar on the bottom between 0 and 500, because it just to highlight that the 500 important prefixes always converge first. It's important because if you design, and normally you design on the basis of worst case analysis, if you're looking at the worst case convergence for your most important prefixes, you need to look at the yellow dot for the point number 500. And this is much different to what you should do if you would have no prioritization, in which case you would need to look here. And you see that the difference between the two is quite important. The next thing we learned from this experiment is that the spread is small. So the spread is the difference between the minimum and the maximum. And we try to work a lot on this to increase the determinism of the convergence behavior. So finally, we can look at the BGP results, the 3 last points. The first one to the left is the BGP next stop. The 2 other points are the loss of connectivity measured to BGP destination. And what you see from here is that the loss of connectivity for a BGP learn prefix is actually the same as the loss of connectivity to its BGP next stop, which is learned in the IGP, which means that the BGP learn prefixes also leverage all the optimization for the IGP. It's an important result. So here we summarize all the test scenarios for the remote versus local, load balancing versus no load balancing scenarios. So we have 4 scenarios. What we plot is the worst case across the 100 iteration, the worst case loss of connectivity for prefix number 500. So it's the last important prefix, it's the worst case convergence measured for our important prefixes. The first 3 groups in blue, red, and I think yellow from here, yeah, are basically engine 2, engine 3, engine 4 plus with the GRP processor. You see that first it's consistent whether you have a remote or a local failure, whether you are load balancing or not, the convergence in the worst case is measured at around 400 milliseconds. And then the second thing we learned from this chart is that the result, if you take the PRP1 with engine 3, is actually much smaller, on the order of 250 milliseconds. So what we derive from this is that CPU power is very important. The PRP1 is twice faster than the GRP, and you see the consequence. It's also an indication for the future on what could happen if the CPU power keeps on increasing. So as I said earlier, it's when you design, you typically test and look only on the worst case. And it's important to do it like this, but it's also important to look at the difference between the average behavior and the worst case. So here, it's for the engine 3 combination with the PRP1, 100 iteration, and you compare the blue results with the yellow results. The blue one are the worst case loss of connectivity measured for the 500 important prefixes, while the yellow results give you the average convergence measured for the 500 prefixes. And so it simply gives you an added margin or safety margin when compared to the sub-second target. So if we come to that point, the result seems pretty good and confirming the sub-second convergence behavior. There could be two questions that would arise. First, it's basically to say, in your lab setup, you look at different scenarios, you have BGP and so on, but you do not consider the flooding impact because you don't have many hubs. Also, you do not consider the fact that the routers could be spread over a continent or multiple continents. Actually, those 2 points are negligible, and that's the purpose of the remaining of the next slides. First, let us look at the flooding impact. We take our unit under test, define it as previously, and we add load to it. We add SNMP probe, and we add 8 BGP flaps per second. The CPU on average is at 35% utilization. We connect the unit under test to 2 Agilent devices. The first one is sending an LSP, and we measure how long it takes for this LSP to be flooded to the second Agilent device. We repeat the test 1,000 times, and we plot the flooding time per hop on the y-axis. So we see that for 90% of the measurements, the flooding time per hop is smaller or equal to 2 milliseconds. The reason for this is that it's important in the implementation of the IGP to make sure that you're going to flood the important LSP before going into SPT computation. The other question was related to the propagation distance. So intuitively, it's quite straightforward to conclude that this is negligible, but we still wanted to analyze it in a more formal way to confirm it. So let's first define the propagation distance. So again, there was some animation, but let's see what we wanted to do. We have initially a stream going from left to right that initially goes via the green path. At a certain point of time, the link between F and Z is going to fail. So we will have a convergence event, and the traffic stream will eventually be routed according to the red path. We define F as the failure node. It's the node that is locally connected to the link that is going down. We define the rerouting node as, intuitively, it's easy to think that the rerouting node is the point where the two paths diverge. It's the point where the rerouting occurs. And so if we define it like this, we can define the distance between the failure and the rerouting point as here being 1 hop, and being, in terms of propagation, between the propagation through that link. The propagation is more or less 5 milliseconds per 1,000 kilometers of fiber. Actually, if we would have time, we could show that this intuitive definition of R is actually a worst case. There exists better case for a rerouting node than this one. So the results that you will see are worst case, and we are recomputing them to have a better analysis. Still, the results confirm the intuition. So one of the lead customers that work with us gave us the topology. It's a worldwide tier 1 ISP. They gave us the full worldwide topology, the full traffic matrix, and we knew the propagation distance between any two routers. So we have failed the 340 most loaded links on the network, and for each failure scenario, we have computed the distance as previously defined. We have weighted each of the distance as such computed by the amount of traffic on each flow, as we knew the traffic matrix. And what you see being plotted here is basically the results of all these computation. What it says is that if I remember well, 50%, for 50% of the cases, we have a distance of 0 hop counts. So it means that when we have a failure, it's the local node that will locally reroute. And we have, for 95% of the cases, the hop count is smaller or equal to 3. So it means that you really don't need to flood very far. And so the hop count that influences the flooding time is very small, bounded by 3 for 95% of the cases. We take the same analysis and we look at the propagation distribution. What we find out is that 78% of the cases, the propagation distance is 0 milliseconds. Why? Because it's either a rerouting in the same node itself, or it's a rerouting that occurs in the POP. And we find that 92% of the cases are going to have a distance to the rerouting node which is smaller or equal to 35 milliseconds. So this confirms that the flooding time, if you indeed flood well before you run SPF, and the propagation distance are negligible, and so that the results that we presented are actually relevant. So the conclusion is that sub-second convergence for ISIS is realistic and is actually conservative, and that the technology has significantly improved. So the question that would arise now, I guess, is why is it possible? So the way we work in our project is basically we have optimized all the components that are involved in the convergence behavior. We don't have the time here to explain all of this. It takes typically 1 day. But I'm going to highlight a few key points that would come to mind most frequently. The first one is D. D is the link failure detection time. We leverage POS. POS is based on SONET and SDH, which will discover the failure in less than 10 milliseconds. So it's a very fast failure detection system, and we leverage it. The only questions that still is present is how long does it take for the discovery of the failure to be communicated from the hardware that is going to detect it very fast to actually to the CPU where ISIS is going to be triggered for its convergence. So we actually did this test, and this is for a unit under test equipped with an Engine 2 POS line card. Again, it's the same configuration with SNMP load and 8 BGP flaps per second. The average CPU time was 35%. We repeat the test 1,000 times, and we measure the time, the time between when the hardware on the line card finds the failure and when on the processor the ISIS convergence is triggered. We find that in 90% of the case, the time between the two events is smaller than 8 milliseconds, smaller or equal to 8 milliseconds. So overall, you would have up to 10 milliseconds to discover the failure in the SONET SDH layer, plus on the order of 8 milliseconds to communicate it to the processor. Now, a question that could arise here, but also for the flooding time per hop, is what is the reason for the rare points or the rare measurements where actually the detection time or the flooding time is actually larger? So what is the reason for this, and is it important? So the first question, the reason for this is that the worst case is going to be on the order of 50 milliseconds. Why? The worst case would happen if you would have a process of the same priority as ISIS that is scheduled on the CPU just before the convergence even occur. And then on top of that condition, you would need that the process that be scheduled is actually a very busy process that would have to keep the CPU for 50 milliseconds for its allocated time slot. So it's rare by itself, and this is, you can see it in the distribution here. The worst case is very rare. The next question that could, the next question, thanks. The next question is it important? And the answer is no, for multiple reasons. The first reason is that, first, it doesn't occur frequently. Second, 50 milliseconds is 20 times smaller than the objective that is 1 second. Third, in reality, in an IP network, it will happen even less likely than in these measurements. Reason is that for a failure detection to actually show this a detection time larger than 8 milliseconds, it would need to occur at the same time on the two routers connected to the link failure. And for the flooding, it's even worse. Because of the meshing of an IP network, you have many flooding paths between the failure node and the rerouting node. So for the worst case to occur, you would need to be extremely unlikely because it would need to occur for the same LSP on all the nodes across all the possible flooding paths. So for these three reasons, I think that these rare points are not important. And anyway, it's 20 times smaller than the target, which is the seconds. The next topic that would be discussed most likely if we talk about convergence is shortest path tree computation. How long does it take to compute Dijkstra? The Dijkstra implementation normally is in n log n. We connect our unit under test to a cloud where we control the size, and we measure the time it takes to compute the shortest path tree for the full cloud. We find out that actually the relationship between the SPT duration and the number of nodes is pretty linear. For the PRP1, it's on the order of 59 microseconds per node. It means that if you have a topology of 600 nodes, you will compute your full SPT in 35 milliseconds. So this is with a PRP1. If you remember one of the first slides, where we had an initial delay on the order of 150 to 280 milliseconds, it was with the GRP, and with a cloud of 1,000 nodes. So the GRP is twice lower, and 1,000 nodes, it means that the SPT computation in that case was 100 milliseconds. And so it confirms the reason why you have such a small initial delay. Now, again, if you have a topology of 600 nodes, running on PRP1 and you do a full SPT, it's 35 milliseconds. But actually, in reality, it will be lower than this. Why? Because we don't do a full SPT, we will do an incremental SPT. So we will compute the graph only for the nodes that have been impacted by the failure. So the 35 milliseconds by itself is also a worst case, and the reality will be better than this. Conclusion. We have presented test results that show that sub-second ISIS convergence is realistic and is conservative, and the technology has significantly improved. Thanks for your attention. Any questions? Welcome.
Hi, have you done any lab testing looking at how this would work or benefit in cases of route redistribution? So does incremental SPF provide a benefit if you dump 10,000, 20,000, 100,000 routes into the router to letting it deal with that gracefully, you know, do some computation, pass on the updates, not get bogged down just doing, you know, an entire network recomputation for every update or so?
No, the reason is that we have, I would say, five, 6 lead customers, and so we're focusing on the testing for these customers. Also, with the experience of the type of designs, the design that you mentioned is very rare, to almost unknown for me. So, I mean, I would be interested to test it if it becomes real, but at this time I have not yet tested it.
Okay, it doesn't happen very often, but when it happens, it's very bad. So,
yeah,
but I'll pop you some email.
Excellent. Yeah, but it's also very good to have suggestions like this because we learn a lot from any feedback, so it's welcome.
I just had a kind of a related question. I was wondering if you had in your study of the problem kind of built up any design guidelines for IGPs if you want to build fast converging networks. I know that the reason I'm asking is because when we were at Sprint and we were driving a lot of this work, as you know, we found that some of the sort of fast convergence features weren't really operative in our network. Like incremental SPF really didn't help Sprint Link that much because of the topology of the network and so forth. So have you been able to distill guidelines from that work?
Yes, actually. So it's in 2 points. There is a design guide that comes with this presentation. It's based on all the work we have done and the interaction on the different designs, so that there is some mileage or experience behind the design guide. And then the second point is that on incremental SPF, the benefit itself, indeed, it's unknown. It depends on the topology. But in all the tests that I showed, I never capitalized any benefit from incremental SPF. I was always running a full SPF. So if there would be a benefit, it would be coming on top of everything, but it's not included.
Right. Thanks.
Thank you. Thank you.